Well, it's the last day of class, and I know you should be feeling really happy, but I know you're probably stressed out thinking about all your finals to come. So hopefully, by the end of this class, you'll feel a little more prepared for this final, which is really just exam 3. So first, I just want to remind you, you just have 2 things left: a homework on what we're covering today, and yesterday what we did, just the non-parametric stuff, and this bonus survey. They're due tomorrow night. And your study materials for the final, both the study guide and the practice exam and key, is up, and we're going to go over those today. And there's also practice homework, all the homework from this section, which is really only 6 lectures, 6 Tuesday, Thursday lectures. So it's really not much material. There's not much homework, but it's up on Lon Kappa. So you can do it again if you want. Now there's also office hours this week is Tuesday is today, tomorrow, and reading day, 3:30 to 5. Some people are complaining, why do I keep do this? Why don't I write the name of the building? It's because the building has no name. Sorry, it's just next to Cocomera. Maybe I should draw a map for you, but it's between Cocomera and Convenient Care, and it's a building they put us in with no name. It just has an address. And the address sucks because if you do this on Google Maps, it will take you over to the English building. So that's why I always say next to Cocomera. And next week, it's going to be Tuesday's your final. And so I thought Monday would be a good day to have some office hours for your final being the L1 section. And then Friday is the online section's final. So I thought Thursday would be a good day to have office hours. So that's when we're having them. And probably on the second floor because I expect it to be crowded right before the final. So and come, if you want really individual help, there'll probably be a crowd next week. So individual help, just come early. Now, this grade calculator, and just go to our syllabus and scroll down here, and you can click here for the grade calculator. What is that? Well, you put in your exam 1 grade from Compass, or if you know it, let's say it was about, I think that was the average, and the exam 2 grade, that was the average. Of course, yours is going to put in your own. And the homework percentage, and the bonus percentage is hard to figure out, but you probably can estimate something because you haven't turned in your notebook yet. And the total bonus doesn't appear on Compass yet, but I'll do that after I input today's iClickers. All that will be left is bonus survey 5, so I'll give the total up until then, because it's kind of a little bit difficult to figure out with the pre-lectures and stuff. So I'll give you your bonus total tonight, and then you can put it in, but for now you can estimate it. Let's say you think you did about, 70 out of the 100 points. And this is your wanted course grade, overall course grade. So let's say with all this you want a straight A, and you want to see what you need to get on the final to give you that. So a straight A, the lowest straight A is 93, and we'll see what you need to get. So you calculate. So you would have to get a 97 because you didn't get a straight A on these. That's why. Maybe you can see how it changes to turn in your notebook or to increase your bonus percentage, etc. Let's see if you had this and you wanted to get just an A-. So then you would do that and calculate, and then you only need an 83. So you can estimate, of course, if these were higher, any of these were higher than, or lower. Let's see if it was, if you got only a 70 here and a 75 here. But you're doing really well on the other stuff. And maybe you even do more on the bonus here. And you want to get, let's say, a B. What do you get? What do you need? Whoa, that's easy for you. Let's say you wanted to get a B, a straight B, etc., a B plus. So what I'm trying to do is just let you know. I know that you're really stressed out, and I just think about what I would want if I was a student. I would want this in each of my classes so I would know how much to study, basically. Otherwise, this is crunch time and you have to allocate your time. So this is just to help you gauge your how much you need to study for this class compared to other classes. Now, don't get overconfident. Some of you are going to get really overconfident. I've seen it happen over and over again and just think, oh, all I need is like a B+ to get an A or something and blow your A. So don't get overconfident. So, is this mic on? Can you tell? Doesn't seem like it's on. Hold up. Yeah, it's on, isn't it? Okay. All right, so now let's go. Any questions on that? All right, so let's go straight to the document camera now. And what we're going to do is finish up the end of the nonparametrics and then look at the practice test. So here we left off here on page 218. We finished this page on doing the Wilcoxon Mann-Whitney rank sum test. So what are we doing? This is the nonparametric equivalent of the two-sample t-test. And we're calculating a U-test statistic here. So what we did was we got these test statistics right here, and we said, with all these nonparametric tests, if the sample size is big enough, you can go ahead and do a z-test or a chi-square test. And that's what we did. All right? But now, if the sample size is small, you really should use these exact probability distributions. So I just want to show you on the next page the one for this Wilcoxon Mann-Whitney rank sum test. So here we are on page 219. So this is where we're starting today. All right. So remember what we're doing. We're changing all their actual numbers to ranks between 1 and n, however many numbers you have. So what we're doing here is we're going to use the exact probability to compute p-values when the sample size is really small and the central limit theorem doesn't kick in. So you can't approximate it with z or chi-squared. So when sample size is small. And small, we did the cutoff for small, like less than or equal to 7, but I'll tell you what the cutoff is, okay? I mean, I'll say, when I say small, you don't have to, it's not exact. It's just the tables go a little further. All right? So now, what do we do? So for small sample sizes, what's the problem? The normal curve is not a good approximation. For any of these nonparametric tests, when the sample sizes are really small. But what the value of the nonparametric test is, it's not a problem. Because once you convert the data to ranks or counts, the numbers are so simple. Like with a sample size of 4, it's just numbers 1 through 4. The numbers are simple, that it's not hard calculating the exact probability distributions by hand. And you're not going to have to do this one by hand. These are all the U-statistics for different sample sizes. And the probability of, this is the critical values we'd need. There's tables available for the exact probability distributions for the U-stat, but not the rank sum. So once you get the U-stat, this is how you use the table. So these are the critical values to reject the null, but it's for the smaller one. Okay? The tables below give the critical values for just the 5% cutoff. And don't get worried here, I'm introducing this on the last day. You're not going to have this on the final. You're not going to have to do this. I just want you to understand what it means when I say the exact probability distributions. It means they calculated mathematically what the chances are to get various U-statistics, and these are the cutoffs for the chances less than 5% when the null is true. So these are your critical values, okay? And so how do you read this? Because you will encounter it often if you ever do nonparametric stats. So it's for the smaller U-stat, okay? So it's a little bit different than usual. We want to see if our smaller U-stat is smaller than these critical values. Okay, so let's write that down. So if the smaller U-stat that we get, which we got on the previous page, was equal to 27.5, that was our smaller one, is less than the critical value, I'll put a star here, then we will reject the null because it's really extreme. If this smaller one's really low, then the bigger one's really high. So how do we know how to read this table? We have to find the critical value here. Well, that depends on your sample sizes, okay? So it says N1 and N2 are the sample sizes of the smaller. So this is the one, this is sample size for the smaller group. Why isn't that? It's hard to read. And this N2 is the sample size for the larger group. Okay, so in our case, we had the larger sample in the previous page. I'll just remind you, they weren't the same size. Group B is 1, 2, 3, 4, 5, 6, 7, 8, and this has 7. This one had the smaller statistic, even though it had the large U-statistic, even though it had the larger sample size. So this is equal to 8. So we look here. That's our bigger sample size, and this one is 7. So right here is our critical value. So if it's less than, is 27 less than 10? No. So we cannot reject the null. And we knew we couldn't reject the null. We don't want to reject the null. Remember, these are exam scores. I want them to be the same. No, so we do not reject null. Looks like those two exam scores came from the same distribution. So that's the idea. We said we were going to, so to reject the null, it has to be less than. I should say that. To reject the null, that they're the same. If they're really different, then the smaller U-stat has to be less than the critical value. Less than. The smaller U-stat has to be less than. And ours was bigger. 27 is bigger than 10. I said we were going to skip this, but I think it'll help you to understand and to do better on the final. If you just think about, let's skip this, it's kind of hard, but let's do a different problem instead and see if you can, how would you rearrange the exam scores on the previous page to find, I say to be closest to the critical value without going over. How about to find, so group, let's just say group A has the smallest possible U-stat. Okay, how would we do that? So the group A has the smallest possible U-stat. What do you think you would do? We have these numbers here, and how would you rearrange them? Wouldn't you, the smallest possible U-stat would be if all the lowest numbers were in group A, and all the highest ones were in group B. So you would rearrange the scores so that this is the lowest one, the next lowest one, etc. I'll just do that. The next lowest one would be 60, then 65, Then there's 70 and 70 are tied. 1, 2, 3, 4, 5. And then we have just the next two lowest ones, 75 and 79. So these are ranks 1 through 7 here. And then what would be these for group B? The next one is 81, the next highest one, then 85, then 88, then 90, then I'm here 92, 95, 96, and 100. That should be 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, yeah. So that's what we do. Now, what would the U step be? The U would be what? How many times do, these are all the lowest. In ranks, they're 1 through 7. So what would be their U count? U means how many times each one of these outscores those. So how many times does 11 beat any of these numbers, does it? 0 times. How many times does 60 beat any of those? 0. They're all the lowest, so this is the lowest possible. Okay, does that make sense? So your U count would be 0 when you add all those up. And by the way, what do you think these highest would be? Each one of these, 81 beats all 7. 85 beats all 7, etc. So you'd add up, all of these would be 7, and there's 8 of them. So it's 8 times 7, and that would be 56. And that makes sense. So you'd have 0 and 56, and the two have to total 256. Remember, the total is 7 times 8. So that's the idea. Any questions on that? Any questions? Okay. These are just every one of these. It's hard to read, but I just rearrange these scores so that they're all the highest. And then each one of them has a U count, a U score of 7, because they beat all 7 of those. 7 times 8 is 56. All right? And if you did the ranks, it would just be the numbers, you just put them into ranks. Yes. What's the difference between this one and that question? Yeah. This one wanted the one closest to 10 without going over. This is the lowest. Oh. You can find them equal to, you can find, it's just, there's multiple ways you can do this one. Okay? His question was, what's the difference between this question and that one? This one I wanted the very lowest. I wanted the closest to 10, the critical value without going over. And I won't ask, that's hard. Okay, we're going to skip that one. So now I said we're going to skip this. And now we're on the Kruskal-Wallis test. So this is the test we just did. The one we just did is the nonparametric analog to the two-sample t-test. So you use it when you have two samples and you want to compare them, and they don't come from normal populations. What if you have 3 samples, 3 groups, 3 or more groups, and you want to compare them? We can't use that test. We have to use the equivalent of an ANOVA. So this is when you're comparing 3 or more groups here. 3 or more groups. I should highlight that. Excuse me. 3 or more groups here. Okay? And you can't use Z. So we're not going to do a Z test. We're not going to have an approximation that's a Z with more than 2 groups. So our approximation here is going to follow a chi-square distribution. Okay, so it's the non-parametric version of ANOVA. But we can't It has the advantage of not needing the assumption of underlying normal populations like ANOVA does, and that's why we're doing it. Now, we can't use ANOVA and an F-test because the exam scores that we're looking at aren't normal. We know they're not normal. They don't follow that kind of distribution. None of our exam scores do. Okay, so it's going to be exactly like the Mann-Whitney, except we have 3 groups, and we have a chi-squared test because we have 3 groups. We can't use the Z. We have exact probability distributions when it's small. For small samples and for big ones, we use the chi-squared. All right, so let's look at this. So what do? It starts off exactly like what we did before. We change all these to ranks. So let's do that. Change them all to ranks. I did them for you here already. You don't have to do, this is just to help you. You can just eyeball it and see, okay, this one, the first, that's the smallest. And then this is the second smallest. And then 50. Whoops. I did that wrong. This is the second smallest. And 50 is the third smallest, right? I'll just start it out. I'm just putting them in order. I did it here already. So 60 is the fourth smallest. Then 70, you have to be careful again. There's 2 70s. So they would take the 5th and the 6th place. So what do? We give them the average of the 2. So this is 5.5. And this one is 5.5. Okay? So then you go 4, think of it as 4, 5, 6, and then the next one will be 7. So this one is 7, etc. So we do all that, 7, and then we have 8, and then we have 9, then we have 10, sorry, and where's 11 is over here, and 12. Where is 12? 12 is, am I doing this right? Yeah. 12 is here. And then 13 and 14. 13 is here. And 14 and 15 are here. Okay. So now we just add these up. 1, 2, wait a minute. I should have 1, 2, 3, 4, 5. I forgot to do 16. 100 is 16. You know, to avoid that careless mistake that I just did, remember you have 16 numbers. Count them. 1, 2, 3, 4, 5. So we'll say NA is equal to 5. 1, 2, 3, 4, 5. So we have NB is equal to 5. And 1, 2, 3, 4, 5, 6. Okay. So now you see that you have 16 numbers. That means that your biggest number should be 16. You're going to go from 1 to 16. So if it doesn't end up that way, you know you made an error. Skip something. All right? Any questions so far? Are you good? So now we just add them up. And I added this up. This is plus 16. And I got 34.5 for this one. For this one, I added them all. And I got 40.5. And this one, I got 61. All right. So those are your rank sums to check for each group. But let's make sure they add up to what? Do you remember? This is something you absolutely need to know, that the sum of numbers, integers between 1 and n, between 1 and 16, follows this rule. Remember, 1 plus 16 is 17. This is 17. This is 17, etc. That's the n plus 1. And there's n over 2 of them. So this is something you need to know. 16 times 17 over 2, which is equal to 136. So let's check that they add. So check that 34.5 plus 40.5 plus 61 is equal to 136, and it is. So you know you didn't make a mistake. So now we're going to get, now we want to get the expecteds for each group, and this is the same formula we had last time. Let's think, you have to know this too. Let's think of the logic of it. This right here, first of all, n plus 1 over 2. It's the same n plus 1 over 2 here. And this is the average right here of all, this part right here is the average of what? The numbers 1, 2, 3, all the way through n. That's it. That's 17 over 2, 8.5 is the average of all those numbers. Okay? So then, what's this little n? This little n right here is the sample size for each group. And you know that what n is. It's the overall total number. Okay? So this right here is really the same formula, just for all of them. So we would expect, this is our expected value, wouldn't you expect on the average that if you just randomly, our null is what? Our null is that, let's just write it down. The null is that what? All 3 groups are the same, meaning they all came from the same distribution. They're samples from the same distribution. So if they're from the same distribution, you wouldn't expect them all to have the same exact average because they have different sample sizes, and we're taking the sum here. But you would expect each of these numbers, you wouldn't expect all the low numbers here and all the high. You'd say on the average, you'd expect all the numbers to be the average, about the average here, about the average here, about the average here, right, on average. So that's what we're doing. We're saying for each one, we're saying we have 5 here, and we expect each to be about its average. That's 42.5. We got lower than that because we got lower numbers on the average here. Same. Now, how about for group B? That has 5. And it's going to be the same thing. If I was using the formula, I'd say 5 times this formula, n plus 1, 16 plus 1 over 2. So that's 5 times 8.5, and that's equal to 42.52. And this one's going to be what? Not 5, but 6 times 8.5. And that's equal to 51. So these are expected. And that's what we got. And we want to see if these differences between the observed and the expected are big or small. So it's just like a chi-square test. The statistic is this, and this is given to you. If anybody wants to understand this formula, feel free to email me and I can show you the math behind it. But right now, this is going to be given to you, and I just want to, you'll have this. So let's just look how to use it. All right? And it's distributed as a chi-squared. It kind of looks like a chi-squared, observed minus expected squared for each group in the numerator. And this is kind of like over the expected. So let's look at it. So we'll go down here. First of all, we need the degrees of freedom. What do you think? Well, here it is. The degrees of freedom is equal to, as usual with all chi-squared, it's the number p minus 1 or the number of groups minus 1. P and G are the same, so it's just G minus 1 with 3 groups. So 3 minus 1, so it's a chi-square with 2 degrees of freedom. So that's where you're going to be looking for the critical values. We just have to compute this. I'll show you how to do this. So let's just remember what the alternative is. It's that not all 3 groups came from same distribution. At least one of them's different, right? So I'll tell you, this is given to you. Okay, so let's just compute it. It's called the H-statistic. And so we'll say 12. That was that same 12 in the standard error we had before. That's also going to be given to you, that other formula. Don't worry about the standard error for the rank sums. And the U, where was that? I just want to show it to you. This one is the another one that's going to be given to you. That looks very similar. By the way, if anybody wants to understand these, you can just email me, and I'll send you something. All right, so this is 12 over what? 16 times 17, right? And then we're summing up 3 groups. So let's do that. 3 groups. The first group is what we're doing is we're saying this is our observed and that's our expected. So it's just the difference between those two squared. So that's 34.5 minus 42.5 squared over its sample size, 5. And the next one's going to be over 5, and the next one's going to be over 6. So it will look like that. So now we have to look at the next one, which is what? This is 40.5 minus its expected, which is 42. These two have the same expected. And the last one is 61 minus 51. All right, so we'll just compute that. I just want to show you one thing. You can check your work this way, or you can understand the reasoning for squaring. Remember if we don't square, these differences are going to sum to 0. Watch. That's negative 8. We square it. That's negative 2. And we square that. And that's 10. And if we didn't square it, as usual, that's how you know you did it right. They add to 0. Negative 8 plus negative 2 plus 10 is 0. These would add to 0. Okay. Oops, this is over 6, though. I'm just saying those numerators would. And now, finally, a lot of computation. You're not going to have to do so much on the final. But this is 1.344. That's what I got. And that's distributed as a chi-squared statistic. So, do you know right off the bat whether that's going to be significant? Think about it. Remember the chi-squared? It's going to be, look, it's only 2 degrees of freedom. So it's going to be like really lopsided. It's going to be like one of these ones that goes whoa like that, all the way like that, right? Now, when the null is true, we'd expect the mean to be about the degrees of freedom, so about 2. What's our chi-squared? Our h-stat. Our h-stat is right here at 1. Why don't we write it here? H equals 1.344. That's where we are. And our p-value is all that. That's going to be a lot. That's a whole lot. That's going to be way bigger than 5%. That's going to happen as an everyday occurrence. So this is just so consistent with the null. When the null is true, we're going to get this all the time. We expect to get even bigger too. But if we get the differences are so big up here, like if we had, let's say we had a tiny, these were really giant differences, then we'd reject the null. But where's the critical value? Well, degrees of freedom 2, remember how you do this, it's just our usual. If the differences are so big that when we do that, square them and sum them up, here's our critical value for 2 degrees of freedom, right here. So 5%, if we wanted to, this is a 5% chance we'd get this or bigger. So at 5%, it's 5.99. So let's just say that was about 1, 2, 3, 4, 5, 6, about right here. That is our chi-squared critical at 5%, and it's equal to 5.99. So from here, this is 5%. We have all this plus 5%. So our p-value is much bigger than 5%. So we're not going to reject the null. Okay? Our h, so we're comparing h has to be bigger to reject the null. H is 1.34, and it's less than the chi-squared, which is 5.99. So our p-value is much greater. So we cannot reject the null, and our data is consistent. So if these were exam scores, I'd be very happy. It means that we're not rejecting that. We think all groups came from the same distribution, that all the exams are equivalent. So we cannot reject null. We have a huge p-value. On this side, if your statistic is so extreme, so rare, you reject the null. On this side, you cannot reject the null. You're saying, hey, I'm going with the null, which I'm very happy about. Does that make sense? All right. So that's that one down. And let's see where we're at. Can I turn the page now? Everybody's good? All right. Look where we're at. We've done, just turn to 223 for just a second. So here's a summary, and I want to show you what we've done. We just have one left to do. We have 3 non-parametric tests. We've done this one and this one. This is equivalent to the 2-sample T. This is equivalent to the ANOVA. Now we're going to do one that's equivalent to a correlation coefficient. It's just changing, doing the same thing, changing to ranks, and computing what's called the rank order correlation coefficient. So let's do that, and then we'll do some problems, practice problems on these non-parametrics to give you some practice. All right. So it's the non-parametric version of the regular correlation. So all you do is you replace the actual values with ranks. So imagine these were your actual XY pairs, okay? How would you compute the correlation coefficient? Spearman. To compute the regular one, you change all these to z-scores, right? And a regular correlation coefficient is R equals, you change to z-scores, take their products and divide by n. The Spearman one is exactly the same. You do this, but you once you convert all these values, once you convert the values to ranks. Let's do that, and I'll show you what I mean. All these to ranks. So there's 7 pairs. So the x's are going to run from 1 to 7, and so are the y's. I already put them in order for you with the x's. If you can see, this is the lowest one. This is the second lowest one. So we've got I just put them in order. Sorry, that's just a blank there. All right, so now we just have to fill in the y's. So which is the smallest y? Just by looking at it. 40 is the smallest y, so that gets a rank of 1. The second smallest is 45, so that gets a rank of 2. The third is 61. The fourth is 70. And then what comes after 70? 79 up here, right? So that's the 5th, that's the 6th, and that's the highest. So that's what it looks like. That's how we converted them to ranks. And now when you work with the ranks, it's so much easier, because look, these numbers are so easy to graph, and it's very easy to compute correlation coefficients with them and to get exact probability tables. All right? Any questions on that? All right. So if we actually wanted to compute the Spearman, what you do is just, okay, what do we have here? We have, instead of putting these numbers, 7 and 45, we have 1 and 2. So 1, 2 for the first point, 2, 1, 3, 4, 4, 3, 5, 7, 6, 5, and 7, 6. And it's super easy to graph these if you wanted. Then you would convert to zx and zy. So you take the average of both of these. They're the same numbers, so the average is going to be right in the middle, 4 for both of them. And the standard deviation is going to be the same for both of them, and it's 2. I just happen to know that, and I would give that to you. All right, so there's that. And now we'll just change them to z-scores. So you say what? Value minus average over the standard deviation. So you get negative 1.5, right? And this is what? 2 minus 4 over 2. This is 2 below. So it'll be negative 2 over 2. This is negative 1. This is 3 minus 4, negative 0.5. This is exactly at the average. This is 1 above divided by 2, so that's 0.5. This is 1, and this is 1.5. And you can do the same with the y's. So I'll start here. So I have 2 minus 4 over 2. So that's below average. This is negative 1.5. This is right at the average. This is negative 0.5. This is above the average by 1.5, above the average 0.5, and above the average by 1. All right, now you just multiply them. So we have 2 negatives multiply 1.5. This is 1.5. This is 0, 0. This is 0.75, 0.5, and 1.5. All right, so now we're just summing them. So our observed rank sum is what? We'll just do that. So our observed, what we see, correlation coefficient, R, and this S doesn't stand for a sum, it's a Spearman. This is the regular correlation coefficient, this is our Spearman. And what we observed is what? We add all those up together. We're just doing those. So we add them all up and we get 5.75 over however many there are, 7. And it's very high correlation. So that's what we observe. Okay? Now, we're going to do the normal approximation here, and I'll tell you when I would like you to do it and when not to. For 7 or more pairs, the distribution of R under the null is approximately normal. We have enough. There are tables for the exact probability distribution, which what do? They do every possible combination of how you compare these up and the probability of each. For example, if we got a perfect correlation, these would be 1, 2, 3, 4, 5, 6, 7, and there's only one way to get that. So it'll be 1 out of all the possible ways there are to pair them up. There's 7 ways, 7 times 6 times 5 times 4 times 3 times 2 times 1. So out of that would be your exact probability distribution, the chance for getting a perfect correlation, etc. They do it for each one. But here we're going to use the normal approximation, which makes it super easy. Now, in the population, the correlation 0 versus the alternative, it's not, and we have this observed one. And it's our usual, our observed R minus our expected over the standard error for the RS. This will be given to you, the standard error. So you don't need to know it, you just need to know how to use it. It's easier than our other one that we had before. Remember our other one? You don't have to know this, but just to put it here, just to compare, we had this, the square root of 1 minus R squared over the square root of n minus 2. Let's not worry about that now. It'll confuse you. Let's just remember this is easy. And it's given to you anyway. So what are we doing here? You have this observed slope minus the expected. The expected under the null is always 0 with the problems we've been doing. And then we just have to compute that. That's super easy to compute because n is what? Our number of points, 7. So we just have 1 over the square root of 7 minus 1. 1 over the square root of 6. So I did that, and I got this. That is our z. When you see that z, 2, you should think 95% in the middle, right? Now it's two-sided, so we're right on the borderline. It's a tiny, tiny bit higher. So if I looked that up in the table, 2.01, it's about 95. It's a tiny smidgen bigger. Let's look. Actually, 1.96 is 95 in the middle. Let's just look, just to refresh your memory. Okay, 2.01. Well, it's about 95.5, or that's 95.96. I looked it up more exactly, and it was 95. If you said 95.45 would be fine. But I said 95.6. Okay, and it makes the math a little easier. That's between, on z, between, what's this, 2.01, and that's 0, and that's negative 2.01. And that's where, for the rank Spearman, we expect 0. That's where our observed lined up when we changed it to a z-score. Okay? So we have this piece and this piece, which is, what is that? So our p-value is 100% minus the middle area, 95.6%, which is 4.4% for the two tails. So we just reject the null. We're not so sure. So we'll just say we barely reject the null. We reject the null because it's less. You know, we don't have that. It's not so extreme, and it's a two-tailed. We didn't know which direction. For a one-tailed, we'd only have, what do we have? We have 2.2% on both sides. So for a one-tailed, we'd be more sure. But if you want to go by the book, we reject the null at the 5% level, because that's less than 5%, our p-value, and conclude we've got some pretty good evidence that R in the population is not equal to 0. Basically, all we're saying is, I'm going to ask you to be careful on the exam. So I would say what you really are concluding, I should write it down for you right here. What you really conclude is, if the null was true, the conclusion really should be, even though you know we're sort of deciding for the alternative, the conclusion really should be that if the null was true, if there was really no population correlation, it was just 0. If the null was true, we'd see this large in H-stat as what? Where's our H-stat? As that. We'd see this extreme large in H-stat, or larger, or even larger, only 4.4% of the time. So we think that's small enough, since it would only happen 4.4% of the time. That's why we reject the null. That's what it means to reject the null at 5%. It doesn't mean we've proved that there's only a 5%, 4.4% chance or anything like that. That's just what it means. Right? That's all. Okay. So now that we've done all that, let's just turn to our summary page. It's a very nice summary here. And just remember, let's see. So the basic big picture idea here is that all those, we don't have to assume normal populations here, right? Basically, all the parametric tests we've done either is, say we're dealing with normal populations or large enough samples. Oh, sorry, so sorry. If we don't have normal populations, we can sometimes transform the data to look more normal. This is going to be on the exam, the data transformation, as we did in part 14. That's the beginning of it, starting with chapters 42, right? We can transform it. Remember, we'll look at some examples of how to do that, because that will be on the exam. But when that doesn't work, the best option is to use the re-randomization techniques. That won't be on the final, that we had that before, or these non-parametric ones that we listed below. Logistic regression is a parametric test, and we just are changing a curve into a different form. So that's a parametric test. These are the only non-parametric tests on this exam, and all of them are going to be rank tests, okay? So that's what we're doing right here, rank tests. And what do we do? It tells you pretty much these are the three. And notice how, okay, so for small samples, all of these, we use exact probability tables. And for these large samples, what do we do? What are we using? We're using chi-squared and z. Excuse me. So we're using z and chi-squared. Why never f or t? I should probably explain that. Okay, so here. For larger samples, and we're using this arbitrary cutoff here, we use z and chi-squared tests. Why? Z and chi-squared, they're distributed as z and chi-squared stats, okay? Why? Because once the data is converted to ranks, we've got, that's basically what? Just integers between converted to ranks. It's always just, if we have n points or n, we have just have integers between 1 and 5. We have data that it's just a uniform distribution. It's very even data. We have data that's so easy, so simple, so uniform, that's close enough to normal. We have data that, is close enough to normal that the central limit theorem kicks in really quickly. So it allows us to use this. And we don't use, kicks in quickly, and we don't need to use F and T because we know the standard deviations of our ranks. They're just integers between 1 and n. So we never use T and F, and we never use them in logistic regression either. We never use T and F. Basically, we have counts here. We just have numbers between 1 and 7. But we never use T and F because basically we know the standard deviation of the ranks. Okay. We're not doing the same kind of estimations that we had. Enough of that. So let's just do some problems now. So I think my idea would be to start with let's just start with, because you really did not have enough practice on the non-parametrics, so I want to start with the practice final, covering just the last, the practice final covering just the last two chapters, 54, 55, and 56. And let's just start questions 14 to 18 on the Spearman rank order, because we just did that. And I just want to make sure you have enough practice on this, and I think it will help you understand it. Okay, because in your homework you only had 1 or 2 problems. So let's look at this. And it says the 4 XY pairs have a Spearman rank correlation coefficient equal to 0.8. Which of the following also have 0.8 as a Spearman RS? Which ones? How do you know? How can you tell? Well, first change this one to ranks, okay? So in ranks, what is this? I lined them up so that this is 1, 2, 3, and 4 for the X's. And which is the lowest Y? This one, so this is 2, 1. The next lowest is this, 1, 2. And now we have, what? 3, that's the biggest one, so that's 4. So that has RS equal to 0.8. Well, which ones of these do? You just change them all to ranks and see which ones look exactly like that. Do you understand how to do that? Do I need to do it for you? Raise your hand if you want me to do it for you. Okay, so everybody knows how to do that one. Next, let's say this is a, pay attention here, because this is will help you understand what's going on. Let's say we randomly sampled 4 points from a large population, and after converting the points to ranks, we got a perfect correlation. Okay? So that means that our observed Spearman rank correlation coefficient is what? You can just look at that and you know it's what? 1. It's a perfect correlation. Okay? And then we want to test this null hypothesis. So let's do this. So our observed is that. Under the null, our expected RS is equal to 0 under the null. Okay. So now it says if we use the normal approximation, let's say we did use the normal approximation, then we're going to do the exact probability distribution, and we're going to compare them. So first, let's do the normal approximation. What is our Z? You have to know this. Z is always observed minus expected over the standard error. We have our observed and we have our expected. Now, what's the standard error? You have to remember, okay, that's standard error. Look at it's going to be the standard error for the rank, for the Spearman rank. And you'll look, it's going to be on your exam. So that will be the formula. It will be given to you on your exam. And to remember what it is, it's 1 over the square root of n minus 1. So 4 minus 1. 1 over the square root of 3. So that is, when you do that, that's like the square root of 3. That's closest to 1.73. That's what it's closest to. So you look here, and I said they rounded to fit the lines on the table, so this would be your answer. So then how would you figure out the p-value? Well, you would just draw the normal curve, right? And you'd look at your normal table, and between z equals 1.75 and negative 1.75 is 92%. That's on the table. And you have to look at this. This is population. It's directional. So I just want this side, right? Because it's one-sided. H, this one, is greater than. If it was not equal to, then it would be two-sided. So that's 4%. Right? 100 minus, it's 4% on each side. All right. Now, you could figure the p by doing the exact probability distribution too. So I gave you, there's 24 possible ordered pairs. You can think about it. If we do 1, 2, 3, 4, there's 4 ways to put the first, times 3 for the second one, the y value. 4, there's, you don't really, it's 4 times 3 times 2 times 1. That's where that 24 comes from. That's how many possible pairs there are. And there's only one way to get it perfect. So if we figured it out that way, it would just be what? 1 over 24, which is approximately equal to 4%. So in this case, they agree very closely. They don't always agree so closely. So I just wanted to give you an understanding of that. Suppose we lost the original values. We didn't see this. All we have left were those. This is like a homework problem you had. All you have is the ranks. Is it possible to figure out what the exact values are? Is it? If I just gave you these ranks? No, because you could pick any number. This just means it's the smallest number with the second smallest number. So it would be an infinite number of possibilities, right? It could be anything. It just means that the smallest number is paired with the second smallest, and the two highest numbers. So the two, like these are the two highest numbers, 5 and 20. They could be anything. They could be 503 and 3,470, anything. They just have to be the highest numbers. So, no. You can't. That's what makes it so simple when we deal with ranks, because that's why we can figure out exact probability distributions. Now, I think at this point, why don't we go to the study guide and do some, I think you should be able to do the rest. You just didn't have many problems on the Spearman. Would you like, let me just give you some on the study guide. Let's go, or do you want to do the let me just do some problems on the study guide. Okay? Just to go over some stuff. And why don't we start? Do you want to start like just with the data transformations? So this is your study guide. I don't know. Let me see if you can see it. You probably don't have it with you, do you? Do you have it with you? I don't even know if you can see it. But basically, it says, all right, let me see if I can zoom in so you can see. So you have this data right here. There were all these islands. Right here is the area of these islands, 13 islands. And this is how many different species of mammals are on them. And you can see like they're all crowded together. You really can't see anything here because it goes all the way up. This is in square miles, all the way up to 800,000. And so all these islands, oh, sorry, you can't see a thing. I'm really sorry here. What? Why can't you see anything? Auto. There. Now you can see it better. Okay, I apologize for that. All right, so as you can see, this area, this is a typical problem where you want to take a log because you have these giant numbers. In order for Borneo and Sumatra to show up, all these other little islands just look like they have zero, and they don't have zero area. So what we want to do is bring these in, do a transformation that, which transformations, here's how if you just looked at the histogram of the area, you see it goes all the way out to 800,000, and all these look like they're zero, but they're not. Okay? So you need to know when you have this long right-hand tail like that, what you want to do is make these bigger numbers smaller. Like if you take the square root of 800,000, it's going to make a lot bigger difference than if you take the square root of 1. That will still be 1, right? So we want to make these all come in. So this would work, and this would work to make this histogram more normal. This is more extreme. This is the exponents. All right? So these two would work. And so let's just write down these two. Make bigger, the bigger numbers smaller to correct a long right-hand tail. This is a long right-hand tail. It's right skewed. It's called right skewed. Okay? So how about these? These all make this do the opposite. These all, you can see they make bigger, the smaller numbers bigger, right? So these are going to make all the numbers bigger. So these make, this looks like this, watch. Like that. So we want to make these, it actually makes the bigger numbers bigger. It makes these bigger numbers bigger. I mean, if you raise this e to the 800,000, I don't even know if your calculator would be able to do that. It would just be a gigantic number. Whereas if you raise e to the, if you take the log of 800,000, then that's just going to be what? Well, it's done right here. It's about 13 or something. So that's what was done here, is like they did two transformations. You first tried one of these, is what I said. You tried one of the transformation, and it was a step in the right direction, but it didn't go far enough. You could just say, it's these two. You could say, take the square root of 800,000, and that's going to be about 90 if you just did it on your... Now, what is the square root of 800,000? It wouldn't be. It would be, if you took the square root of 800,000, it looks like it's about 900. That's about right, a little bit less than 900. Whereas if you took the log of it, it's about 13 or 14. So this is the milder one, and this is really extreme. Does everybody understand that? So this makes the bigger numbers bigger to correct a left hand, to pull this out to make that one more normal. All right, so to correct left skewed, like our exam scores. That's the idea with these. Now let's just do a problem, this one. So after we make the correction, and it says here, so it's pretty much gave it away, this is the log species here and the log area, natural log area. That's what we're doing here. And now look how nice and normal it is. And now they show up. And now Borneo, in terms of logs, is only like 13.5 or something instead of this crazy number way out here. So you can see all the islands, and it looks good. And so this is the equation for that line right here. So that's our log equation, and this is the standard deviations of the errors around, the spread around that. So now we're going to say this island right here has this area. So plug it in there, and to get the log of the species. So that's just super easy. So we'll do that. So we'll just plug in 450 in there. So we'll just say 1.6 plus 0.23 times the log of 450. And I did that, and I got 3.01. You can check on the graph. Does it show up? It's this one right there. So it looks like about 3.1, yeah. And if you took the log of 450, it would be right about 6. All right. So then, what about the number of species? How do we get that? Well, we just exponentiate, so this is going to be e to the 3.01. So then we get 20.2 is the number. Okay. Now we want to do these confidence intervals. I guarantee you you're going to see these both for logistic regression and for here. You're going to get these symmetric around the log and asymmetric around the number. So how do we do this? The confidence interval for part B above, for this, that's going to be 2 steps. We're going to have to do it in 2 steps here. Let me just get a piece of paper here for you. So, I mean, basically what we're going to do is first, just so we have more room here, is first, the first step is we're going to take a 95% confidence interval around this, around the log. So for the log of the species. So we do that super easy, just the usual way. We're going to add and subtract 2 of those because it's 95%. So it's going to be minus 2 times 0.2. That will be one endpoint. And the other one will be 3.01 plus 2 times 0.2. All right, so that's what we're going to do. And so what do we get when we do that? That's 2.61 is one endpoint. And the next one is 3.41. But that's for the log. That's not what they asked for. That's not what they asked for. So what you need to get is then exponentiate those. So you do e. So the second step is to get it for the species. So that's going to be e to the 2.61 and e to the 3.41. And then I got this is 13.6 and 30.27. Let's put that in here. So that's 13.6 and 30.27. All right. Now, and I told you to use 2 here. How could I check that? If you wanted to check that, you're going to check what? Not that 20.2 is the midpoint of that, but check that the square root of 13.6 times 30.27 is equal to 20.2. That it's the geometric mean. Sorry, that's kind of messy. Does anybody have any questions on that? The study guide has the same thing worked out, or maybe a slightly different explanation worked out, but but does any questions on that? Please don't say, 20.2 plus or minus 2 of these. All right, another island has a 95% confidence interval equal to that. For the predicted number of species, what is the predicted number of species? Well, that's its confidence interval for number. So we could just check it's a predicted number, must not be the midpoint of those 2, but the geometric mean. So it'd just be 11.23 times 25, the square root of that. And if we do that, I got 16.76. These aren't the only ways to do these problems. I show you another way, on the 2 ways on the study guide, but I think this is the simplest way. All right, now, this is really important. How do we change from a log species to an equation in terms of species and area, not log area? So here's species. I want to change these 2 right here into species and log area. I mean, you might be able to see right away that when you exponentiate, these are going to be your exponents. And we'll do it out. So it would be, you take e to the 1.6. And now, when you exponentiate, look, it gets rid of the log. So now we have area, right? Area to the 0.23. So these coefficients become the exponents when you anti-log. But you can also do it, work it out and just say, okay, so when you get species equals e to the 1.6 plus 0.23 times the log of the area, and that's equal to e to the 1.6 times, and then you say, I should have written that. Let me change it, times let's just do e to the log area. I'm just going to rearrange those for people who are not used to doing this. I feel sorry for people who haven't done it in a while. Times 0.23. Then you can see that this part is just the area. Okay? So that part is just e to the 1.6, e to x, you're anti-logging, so you just get the area to the 0.23. Okay. And let's skip this. It's just more math, and I realize a lot of people just aren't that comfortable with it, and it's not even that important, so just skip that. Okay? Now, let's look quickly at what you're going to have to know for logistic regression. So I'm going to star some ones that are really important, like all these here. Logistic regression, so just make sure you know that the y variable always has to be 0, 1 for logistic regression. The x can be anything, but the y is always 0, 1 for logistic regression. It's like a yes-no question. Favorite colors, not yes, no. Did you get a scholarship or not is a yes-no question. So this would be, and that wouldn't be. It handles y values. So this would be false because it's just y values. Okay. And it's not transforming nonlinear scatter plots. It's just, it's only when you have a 0, 1 y variable, not any nonlinear. Okay, let's see what's really important. I think this problem you should really look at carefully. And you know what you really need to do is look at the explanations for the study guide. Because I put in the explanations are a lot of things that you need to know. I just want to see if there's anything else in the study guide that I don't think is worth looking at besides that one problem. Let's see. I mean, this one is probably not that important. This one, if you have problems with that, it's not sort of important, but not that important. Let's see. This page is really important. Let's see. This isn't helpful, is it? I just want to go through and see if there's anything you can really skip. Okay. I don't think so. I think, I hope the explanations are good enough. If not, just come to office hours, okay? Any last minute questions? Because I know I didn't. The other thing I could do is go over and do a video working out the study guide if you want to see that. Would you? You think that would be a good idea? Okay, I can work out the study guide and just because you have the explanations, but you might want to see the whole study guide worked out. And the practice test too. I can do that for you. All right, so I'll get that up. Any of you, I'll try to get it up by Thursday. Okay. All right, well, good luck, and I'll see you guys at the final. And I'm going to send you a lot more information about exactly how to calculate your grades and exactly what you need to bring to the final, what pages you can skip in your notebook, all that kind of stuff. You'll be getting videos about that. And good luck on all your finals. Don't stress out too much.
Where's the final?
I'll post that too, yeah. Good question. I'll post exactly where to go for the final.